Welcome back to the discussion on plant respiration. In the previous lectures, we have covered complexes 1, 2, 3, and 4 of the electron transport chain. These are associated with movement of the electrons downhill. Today, we will discuss the hypothesis which explains the ATP production due to the proton gradient established by the complexes 1 to 4. You will be also introduced to the concept of ATP synthase, considered as the complex 5 of the electron transport. As we have learned, the complexes 1 to 4 are involved in electron transfer that bring about oxidation of NADH and FADH2. The oxidation of these molecules is extremely important for Krebs to continue. As a result of the activity of the electron transfer, the protons accumulate in the intermembrane space. There is electrochemical gradients established across the inner mitochondrial membrane. The membrane carries therefore a differential charge which is negative towards the matrix and positive towards the space. As a result of this activity, a pH gradient, delta pH, is created. We should also remember that due to these changes, a membrane potential represented by delta xi is set up. This is represented by the formula given here. Now, looking at the hypothesis which explains ATP synthesis, we can talk about the hypothesis proposed by Peter Mitchell. He gave the CHEMI-OSMOTIC hypothesis, which is based on the proton motive force, or PMF, generated in the mitochondrial inner membrane. According to the hypothesis proposed in 1961, the CHEMI-OSMOTIC model embraces two features of the electron transport chain. Firstly, it is an electrochemical process with respect to the proton accumulation across the membrane. There is a charge separation as well. Secondly, it is based on the principle of osmosis, where while the protons move, they involve a semi-permeable membrane. As the ATP synthesis is also coupled to the electron flow, the concept is occasionally also referred to as CHEMI-OSMOTIC coupling. It is extremely important to remember that the membrane cannot be left to this charge difference. Thus, the 10 protons which have been pushed to the positive side while electrons pass through the 4 complexes must be transported back. The proton gradient therefore should be dissipated. Now, 3 important points must be taken into consideration before we talk about the backflow of the protons in the mitochondrial membrane. These are: 1. We should remember that the mitochondrial inner membrane is itself impermeable to the proton transfer. So the protons cannot be pushed back simply and need to be carried by certain molecules. In this case, it is the ATP synthase, the enzyme complex, which is also considered as the fifth complex of electron transport chain. Second, the PMF is responsible for the backflow of protons. Third, it is this final movement of protons which leads to the ATP synthesis, which is, in case of NADH, 3 ATP molecules per NADH, and for FADH, it is 2 ATP molecules per FADH. This is the general concept of calculation. However, the concepts have been revised, and we will be discussing about the calculation, the way it is done these days. But before we talk about this calculation, let me tell you that ATP synthase is a key enzyme, and it is oxidative phosphorylation, which we will be talking about in the case of respiration. It is also represented as OXPHOS, all capitals, oxphos. Now, we will be talking about the complex itself, the complex 5. If you look at the diagram, let us take a quick check on the complex. The enzyme complex is also known as FOF1 particle. Remember, children, we cannot say it as F0 or F0. That would be wrong. Subsequent lectures will tell you why we call it as FO. This is the complex 5. The image shows that the complex where the F1 particle faces the matrix or the negative site, it is the catalytic site and the site for ATP synthesis. The FO is embedded in the inner mitochondrial membrane and is associated with the proton translocation. It acts as a tunnel for the movement of the protons from the positive side back to the matrix. So far, the discussion has been quite interesting. However, certain questions remain to be answered. The first important one would be, what do we understand by the downhill movement of electrons, about which we have been talking time and again? This means that the electrons move from high energy to low energy state, or from the low reduction potential to the high reduction potential. You can see the diagram and understand for yourself, confirm for yourself that the complexes 1 and 4, 2 and 3, they all have, whichever you take, they have the differential reduction potential. So the electron would move downhill. Second question is, what is the total number of ATP generated by NADH and FADH2? The total count for NADH earlier was calculated based on the number of protons transported back to the matrix per ATP. It was calculated, about which we will again talk a little later, 3 protons per ATP in the case of NADH. And therefore, if 10 protons accumulated on the intermembrane side, then there would be 3 ATP produced per NADH molecule. In the case of FADH, it is calculated as 2 ATP. However, in recent literature, the count is based on ADP is to O ratio. This is because ATP formation not only requires the presence of ADP, it also requires inorganic phosphate. This molecule again has an additional cost of proton movement. Therefore, it is calculated that 4 protons will be required in the synthesis of 1 ATP, and therefore it comes to 2.5 for NADH, and it comes to 1.5 in the case of FADH2. This is shown in the diagram. Now, the last important question which you may ask is, why should FADH2 give a lesser ATP when compared to NADH, whether it is 3:2 or it is 2.5:1.5? The answer is simple. FADH2 is oxidized by complex 2. So, the 4 protons which have been transferred by complex 1, that is NADH dehydrogenase, cannot be utilized for ATP production by complex 2. The complex 2 has an accumulation of 6 protons only, and therefore, if we take it as 6/3, you can have 2 ATP per NADH2, the earlier complex concept, or it will be 6/4 equal to 1.5 according to the ADP is to O ratio. So this is all about our concept of electron transport chain, where we should be able to say that the complex 1 to 4, they are involved in electron movement downhill. The complex 5 is actually dealing with the protons, pushing them back and helping or coupling the ATP synthesis with this movement. So this is all about the electron transport chain. We will soon be talking about rest of the topics which are left in respiration.